This video covers the last topic in chapter 9, namely p-values. P-values is a very, very important concept, and people tend to be a little bit scared of it in the beginning, but don't stress, it is actually super easy once you get the hang of it. So we're going to go back to all the examples we did in the previous videos and look at how we can calculate p-values for those scenarios. Now, the first thing I want you to do is just check your study guide where you get all the information about what you need to be able to do. So you need to know what a p-value is and to be able to define it. You need to make decisions about your hypotheses based on p-values, and you'll see it's actually quite simple to do that. And then you need to be able to calculate p-values for z-tests and t-tests, and I want you to add to that you need to be able to calculate p-values for chi-square tests as well. So that is part of our additional material. Now, a p-value, all it is actually just a decision rule in terms of probability. So instead of taking a critical value and making a decision based on the critical value, we'll look at a probability and make our decision based on that. So in simple terms, a p-value is just the probability of observing something more extreme than what we observed than what we observed in our sample, if the null hypothesis is true. So we'll do a few simple examples and then we'll get into the different cases. Now, just to give you an idea, here's an example where we are doing a left-sided test and we have a test statistic value of minus 2.5298. Now, we already know, we can see on the sketch what alpha is. So we have our rejection region, and we said, let's say we're using a 1% level of significance. Then we're going to use a critical value of minus 2.326. So that probability, or the area to the left of our critical value, is going to be 0.01. And now all we're doing with the p-value is actually looking at what is the area to the left of our test statistic, and then we can go compare these two. And you should notice here that our test statistic lies in the rejection region, and you can see that this area to the left of the test statistic is actually larger than alpha. So sorry, not larger, smaller than alpha. Alpha is larger than the p-value. So that area there is just the p-value, and if we compare the two, you can see it's the test statistic is in the rejection region, p-value is smaller than alpha, we reject the null hypothesis. Now, another example, let's look at a right-sided test, and for this test, we have a test statistic value of 4. So again, let's say we're using alpha as 0.05, then our critical value is going to be 1.645, and we know the area to the right of the critical value is alpha. Now, if we want to calculate the p-value, that would just be the area to the right of the test statistic. So, and you can see again, the test statistic lies in the rejection region, and that means that probability of observing something more extreme than the test statistic value is actually smaller than alpha. So again, a small probability, you should already start realizing, is we have a small probability here of being more extreme than the test statistic value, so it's unlikely that we'll observe something more extreme than what we've already observed under the null hypothesis. Now, let's look at another example. So here we have a right-sided test. This is now for proportion, and we have alpha is 0.01. So again, we can find our critical value. And in this case, we have a z value. Our test statistic is 1.667. And if we indicate where that is on our sketch, then you can see that it is not in the rejection region. And you'll notice that the area under the curve to the right of our test statistic, and we're looking at towards the right because it's an upper tail test, that probability is quite large. So it's quite likely that we're going to observe another test statistic which is larger than the one that we already observed. Same thing this side with the left-sided test. Rejection region starts at minus 1.645. We have a left-sided test, and the p-value is the area to the left of our test statistic. Our test statistic is minus 0.56, and you can see that green shaded area is much larger than alpha. So that tells us that there is a large probability of being more extreme than our test statistic value. So we're not going to reject the null hypothesis. And that is the basic idea with p-values. So now all you need to learn is how to actually calculate them. But first we'll look at a little bit of theory more. So the definition of a p-value, and this definition, it's quite long and it sounds confusing and all of that, but if you get the concept and you break this down, then it becomes quite simple. So we said here the p-value is the probability calculated, assuming that the null hypothesis is true, of obtaining a value of the test statistic at least as contradictory to H0 as the value calculated from the available sample. And this contradictory is actually just more extreme. So contradictory to H0 means in the direction of the alternative. So if we break this down, a p-value is a probability. Now that means whenever you calculate a p-value, it has to be between 0 and 1. Remember that probabilities cannot be outside this range. So if you do a calculation and you find that your p-value is larger than 1 or smaller than 0, you have definitely made a mistake somewhere. So that is something to watch out for, especially when you are doing two-sided tests. Now, the probability is calculated assuming that the null hypothesis is true. And what the idea with that is basically that we assume nothing is going on when we're looking at the null. So the null hypothesis, remember, is the hypothesis of no change. So pretty much nothing is going on. So we want to see if nothing is going on, how unusual is this estimate or that we got from the sample? In other words, if we look at the estimate as a function and we turn it into a test statistic, how unusual is this value? So if we get a very small p-value, then it means one of two things. It either means that the null hypothesis is true and we observed something really strange and rare, basically an outlier, or it means the null hypothesis is false. And I'm sure you've all heard Occam's razor, which says that the most simple solution is probably the right solution. So we're not going to assume if the p-value is small that the null is true and we're seeing a rare event. We would rather go for the null is actually false, because that's the most logical and simple solution. So what we'll do is we're going to look at the three different types of calculations. So if we have a z-test, a t-test, and a chi-square test. So those are the three distributions that we've used so far for hypothesis testing. So we'll start with the z-test, and we're going back to question 19, the second example we did there, where we did the upper tail test. So we'll start with the upper tail because it's a little simpler doing the probabilities here than for a two-sided test, but we'll move on to the two-sided test next. Now, just a reminder, we looked at this test, we found a test statistic of 1.07, and we did not reject the null hypothesis because you could see from the sketch that the test statistic is not in the rejection region. So now, if we want to calculate a p-value, it means that we want to calculate the probability of observing a test statistic more extreme than 1.07. And by more extreme, we're looking at the alternative, so the direction of the alternative. Now, our alternative says greater than, so more extreme in this case means greater than as well. So we are going to calculate the probability that z is greater than 1.07. So that's now indicated on the sketch, that shaded area in the red. So now we need our tables for that calculation. So all we want now is the probability that z is larger than 1.07, and we can get that in one of two ways. So the longer way is to just say, well, we know that this can be rewritten as 1 minus the probability of observing a z value smaller than 1.07. And if we look at our tables, we go search for 1.07. It's in this line and in this column. So we would go and plug in this value over here. And we end up with a probability of 0.1423. The other option is to just make use of symmetry and say, but we know the probability that z is greater than 1.07 is the same as the probability that z is less than minus 1.07. So if we go to our table here, minus 1.07, that is over there, and you can see that that answer matches the previous one. So you can use these little tricks to just make life a little bit easier for yourself and save some time, especially in a test situation. So that is then our p-value. Now, this was a nice and simple, straightforward example. So whenever you do a right-sided test, you'll just look at the area to the right of the test statistic. If it's a left-sided test, we'll look at the area to the left of the test statistic. Now, in general, this is a comment that you will find in your textbook. So the smaller the p-value, the more evidence there is to the sample in the sample data against the null hypothesis and for the alternative hypothesis. So we've seen that if we look at the rejection region, the further we are into the rejection region, the smaller our p-value becomes. So there's more and more evidence then for the alternative. Then that means that we should reject the null in favor of the alternative when the p-value is sufficiently small. And we might ask, but what is sufficiently small? So we can select our significance level alpha as before, and then reject the null hypothesis if the p-value is smaller than alpha. So we've already seen that happening. And of course, the further away the p-value is from alpha, the smaller it becomes, the stronger our evidence is. So the happier we are with that decision. And if we get a large p-value, it just means it's very likely we would have gotten a test statistic that we observed given that the null hypothesis is true. So there's no reason for us then to reject the null. Now, in your textbook, you will also see figure 9.5, and I've added a few notes here just to make it a little clearer. So in that figure, and in some figures later on in your textbook as well, they talk about the computed Z or the computed T. Those are just your test statistic values. Now, if we look at the sketch here at the top, we can see that the shaded area to the right of the test statistic is 0.0179. So that is just a representation of the p-value. On the second one, this one we are interested in looking at alpha. So alpha is our significance level, and you can already start seeing here where the test statistic lies. It's in the rejection region, so we should get a p-value which is smaller than alpha. So that will be our p-value. So I've just brought the two sketches together here. Now, let's say we changed alpha and we got a critical value to the right of our test statistic, then you can see that the probability of observing something more extreme than this observed test statistic value is now going to be larger than alpha. So in this case, in B, we are going to reject the null. In the second case, we don't reject the null hypothesis. So another way of thinking about the p-value is that it's the smallest significance level at which the null hypothesis can be rejected. So if the p-value and alpha are the same, then we will reject the null hypothesis. So another way of referring to the p-value is to call it the observed significance level. So that is sometimes used in practice. So if I talk about an observed significance level, you'll know that I'm actually referring to the p-value, where if I just talk about the significance level, it's alpha, that we just pick in the normal way. So what's really good about p-values is that most of our statistical software packages do the p-value calculations by default. So you don't need to worry about finding critical values of tables. And you'll see this in Practical 4 as well, where you just plug everything into a function that does the entire test for you, and it spits out your test statistic value as well as your p-value. And you can look at the p-value, immediately know what decision to make. Now, with a p-value, like I said, you can just glance at it and you can see whether it's a close call or whether it's a clear-cut decision. So by close call, I would mean something like this, where we have alpha 0.05 and our p-value is quite close to alpha. So you can see that test statistic is literally just creeping into the rejection region, where a clear-cut decision would be something where your p-value is significantly different from your alpha, and by that I mean significantly smaller than alpha. So you'll see in your textbook they also refer to people talking about the p-value being significant or not significant. And by significant, we mean significantly smaller than alpha. So if we look at these p-values, we're actually getting more information than we would have gotten in the previous cases when we just worked with critical values, because there we would have just said the null can be rejected at a significance level of 0.05, but you don't really know, was that test statistic just creeping into the rejection region, or was it actually quite far into the rejection region? So how comfortable are you with what your sample data is showing you? Because if in practice, if it's a close call, let's say we got a p-value like this one, 0.0498, then what we would typically do is we would say, okay, we need a bigger sample and we need to take another sample because this is too close for comfort. It could go either way, because remember there's a lot of variation in samples. So if it's too close to that critical value point, then in practice we would rather take another sample and increase the sample size so that we get a little less variation in the sample, and then we can make a decision that's a bit more informed. So p-values really useful if you are able to interpret them. Now, let's look at specifically the z-tests. So we have an upper tail test, and like I've already mentioned, an upper tail test, we're looking at area to the right of the test statistic. And this is just from the normal distribution because it's a z-test. If we're doing a left-sided test, the more extreme would mean that we are looking at the area to the left of our test statistic. And it actually doesn't matter where on the sketch the test statistic lies. So let's say, for instance, we have a test statistic that lies here on the left-hand side, but we're doing an upper tail test, then we don't suddenly swap directions when we do the calculations. We still calculate the probability or the p-value as the probability of getting something larger than my test statistic. And you can see in this case, we'll end up with a very large p-value, which means it's very likely, if the null is true, it's really likely to observe what we observed, or even more extreme. Now, same thing goes for a left-sided test. If I observed a test statistic here on the right-hand side, I don't suddenly do my calculations differently. I look at the area to the left because it's a left-sided test. So that is really important. And now we get to the bit that gets confusing. So this is the straightforward part. When we look at a two-sided test, we actually treat it a little bit differently. So in a two-sided test, we are going to consider both directions. But let's say we have a test statistic that lies here on the left-hand side. Then we will take the area to the left of this negative test statistic, and then we also consider, but what if this test statistic was positive? What would that area be then on the right-hand side? So basically, we'll look at the area to the left of the negative test statistic plus the area to the right of the positive test statistic. But that is actually the same area. So it is just 2 times the probability of observing something less than the negative test statistic, or you can calculate it as 2 times the probability of finding something larger than the positive test statistic, which is the statement that is written here at the top. And this is pretty much the most confusing part about p-values. So just always consider the rules. If you have a left-sided test, you always go left. If it's a right-sided test, you always go right. If it's a two-sided test, you just look at the areas towards the tail ends of the negative and the positive test statistic. We'll do a few examples like that. Now, why do we do that? If we're thinking about the normal distribution, let's say we have a alpha significance level, then when we're looking at our rejection region, we're splitting alpha into 2. So alpha is then divided into the two tail ends. And let's say I get a test statistic over here. Then I am technically comparing, if I'm doing the critical value approach, I would be comparing my test statistic to a critical value, which corresponds to alpha over 2. So when I calculate the probability here to the right of this test statistic, I'm actually comparing this probability to alpha over 2. But we don't want to make a comparison to alpha over 2. We're always going to make the comparison to alpha, which is why we can just take this probability and multiply it by 2, and that will give us our p-value. So same thing if it was on the left-hand side, we would have just taken the area to the left, and we would have multiplied that by 2. And you'll see that in the examples as well. Now, we'll do a Z example first, and then we'll move on to T and sigma squared, chi-squared distribution tests. So we originally started this question with a two-sided test, and we ended up with a test statistic which is minus 2.27. So here we can see it on our sketch. And again, our p-value, I've just written it in words here. The p-value is the probability of observing a test statistic more extreme than the one that we observed. So we're going to take that area to the left of the test statistic. So here I'm considering, because it's a negative test statistic, I take the area to the left, and I only do that because it's a two-sided test. And then I'm going to multiply that by 2. So we need to go to our tables again and look for this value on our table. So we go here to minus 2.27, and we get that probability there. And I think I have looked at the wrong one here, so my apologies. I wrote the wrong answer here, so this should be a 6. So let's just correct that quickly. All right, so we have corrected that. So we are going to take this probability, and please be careful that you don't repeat my mistake, and look at the columns quite carefully, that you get the last value correct. So if we go back to the previous slide, then this will be 2 times 0.0116, which is what we got from the tables. And if we do that calculation, it is 0.0232. Now, if we look at our conclusion, or our decision here, this test was done at a 1% level of significance, and you can see our p-value is larger than our significance level, which means that we don't reject the null hypothesis, so we're still making the same decision. And that is pretty much it for the first type of test. So next we will do the p-values for t-tests, and we're going to use 2 different tables for that. So you'll see table A5 is the one that we've used before, and then we'll look at how we can use table A7 as well, which will give us more accurate p-values, and then we'll also have a look at R. But basically the approach is exactly the same as before. So if it's a right-sided test, we're going to take the area to the right as our p-value. If it's a left-sided test, we take the area to the left as our p-value. And if it's a two-sided test, we will look at the area in the tail end and we will multiply it by 2. So I'm not going to do an example of the two-sided test for the t-distribution, but I will do it for the chi-square distribution, and it works exactly the same way. Now, in this question, we were looking at the methods of coiling, so roller straightening and all of that. And we have here the alternative is that mu is greater than 2150. So on our sketch, if we want to calculate our p-value, we want to calculate the probability of observing a more extreme test statistic than 1.333. And we've indicated it there already. And if we shape the area, what we see is more extreme again, determined by our alternative. Then it is that orange area over there. So what we want to calculate is the probability that t is larger than 1.333. Now, if I go to the tables, then you can see here that we start with what we're interested in calculating, the p-value, which is just the probability of t being larger than 1.333. And we need to go to the correct degrees of freedom. So in this scenario, we had 16 observations, so we are using 15 degrees of freedom. And we go search here for the probability that t is larger than 1.333. Now, we know that the t tables give us the area in the upper tail. So if you are doing a lower tail test, you can make use of symmetry, but always draw the sketch. That will help you to not make mistakes. And you'll see in quiz 7, there's a question where I actually ask you to use these tables to calculate an interval for a p-value. So specifically this table, and it'll give you good practice to see whether you understand how to do it. But draw the sketch. It really will help you. Now, if we look for 1.333 on that line, you can see that it lies to the left of this value over here. So as we go to the right, you can see the t values are getting larger and larger. So 1.333 lies over here. Now, we know that the t distribution is centered around 0. So let's first look at this value here, the 1.341. If we put that on our sketch, then we can see that the area to the right of 1.341 is going to be 0.1. And we can see the area to the right of our statistic, in other words, our p-value should be larger than that 0.1. But we also know that the area to the right of 0 is going to be 0.5. So that the total area under the curve is 1, and it's centered around 0, which means half of our values are to the right of 0, which gives us an upper limit for our p-value. So in this case, our p-value is between 0.1 and 0.5. So that is the best we can do with this set of tables. Now, next we will want to go and look at if we can get a more accurate estimate. So we'll go to table A7, which is one we haven't used before. It looks a little bit confusing in the beginning, but nothing to stress about. So again, we're going to look at the same sketch and just visualize what we want to find. And we're going to check that we get an answer similar to table A5. Now, what this table does is it gives us the degrees of freedom in the columns, and then in the rows, it gives us a t value. And in this case, we only have one decimal for the t values, and we'll get back to that. So we just need to go find the correct column to use, and in this case, we are using 15. Because that's how many degrees of freedom we have. And this table then gives us the area in the upper tail to the right of a specific t value, but it's a t value to one decimal. So we're just going to round this one off, and we're going to say, well, we are looking for the area to the right of 1.3. So we know our value t, our test statistic value, is actually here in between 1.3 and 1.4. So you could take either one of these two values as your p-value, or you can be a bit more cautious and say, well, we know that our p-value is going to be in between those two values. So that tells us that our p-value is between 0.091 and 0.107. Now you can see these overlap, but this one is this value is a bit smaller than the one we have over there. So we know the p-value has to be at least 0.1. So we can actually refine this interval a little bit more if we wanted to, and just say, well, we know the p-value will be between 0.1, because that's what the one table told us, and 0.107. So we've made that interval significantly smaller now for our p-value. So I've just written the one exactly as I got it from the table, so I haven't refined it further. Next, I want to show you how we can actually get the exact p-value. For that, we need computer software, and the good news is that you guys have already done this. You just didn't know that you were doing it for p-values as well. But all we want is a probability from a t-distribution. And we know in R, we can get probabilities from a t-distribution using the pt function. What I've input here is just my test statistic, so that's my 1.333, and we could get it even more accurately if we didn't use this rounded value. So in R, there's no reason to type in the rounded value. I would suggest that you rather type in your entire formula and assign that entire test statistic value into a variable, and then you just plug that variable in here. So I've just done this to illustrate the problem. Then we have our degrees of freedom, which is 15. And because we want the area to the right, I've said that lower tail is false, which implies upper tail is what we want. We could, of course, have also left out the lower tail is false bit and just done 1 minus the area to the left. That would give you the same answer. And you can see here, our actual p-value is 0.1012127. So you can see it falls within both of these intervals, and even that narrower one that I spoke of just now. So we've now completed the p-values for the z-tests and for the t-tests, and the only one that remains is for the chi-square test. So like I said, in the z-tests, you can also do two-sided tests for the t-test, and you would approach it in the same way as you would approach for a z-test, or for the example we'll do now for a chi-square test. Now, the example we're going to look at is example 2 from the video where we did the test for the variance. So again, just a reminder that our p-value is the probability of observing a test statistic more extreme than the one that we actually observed. Now, it's easy to see in a t-test or a z-test what more extreme means, because we have that distribution centered at 0, which we don't have in this case. So be very careful, especially if you're doing a p-value for a two-sided test, that you are calculating your probability and that you don't get an answer bigger than 1. So if you, for instance, in this case, would have calculated the area to the left of your test statistic and multiplied it by 2. Remember, we're multiplying by 2 because it is a two-sided test. So if you had multiplied the area to the left by 2, you would end up with a p-value larger than 1, which should set off alarm bells. That should never happen. So we'll look at the values in the tail ends for a two-sided distribution. So more extreme in this case, if we look at the sketch, we can see that 22.875 is actually closer to that critical value, the top critical value, than the bottom one. We know the distribution is skewed to the right, so it's an easy guess that the area that we're interested in is the area to the right. So we need to look at that probability. And to get the p-value, because remember this time, the probability is not the p-value because it's a two-sided test. So we need to multiply the probability by 2 to get the p-value. Now there's two sets of tables we can use for this. So the first set of tables are the ones that you are already familiar with. So we're looking at, for the area to the right of 22.875, and we again need to think about what our degrees of freedom are. And in this case, it's 15 because we had a sample of size 16 and our degrees of freedom are calculated as n minus 1. Now, if we're looking for that probability, we will find it there. So the probability that y is greater than 22.875 is between 0.05 and 0.1. So keep in mind also, we are calling it y. In the additional notes I loaded for you guys, it's just some photos from a textbook that I have at home. They use the chi-square symbol, but we're just not doing it just to avoid some confusion, that you don't confuse the distribution and the test statistic, because there's no upper and lower case and things like that to work with there. So we're just going to work with y for this test statistic. Now, if we look at the values here, and we consider the first value, 24.996, you can see the area to the right of 24.996 is 0.05. So that's what the table tells us here. So then the next value, the other value, or the value on the other side of the one that we're interested in is 22.307, and that value is associated with an alpha of 0.1. Now, we know, if we look at the sketch, we can see that the probability we're interested in has to be larger than 0.05, but it also has to be smaller than 0.1. So that is what I've written there. But our p-value is not the probability because we are dealing with a two-sided test. So we need to take, for a two-sided test, the area in the tail end, multiply that by 2, and that then tells us that our p-value will be between 0.1 and 0.2. So if we go back to our sketch or our test procedure from before, you can see that from this table, we're getting our p-value as a value between 0.2 and 0.1, 0.1 being the smaller one. Now, if we look at our conclusion and our decision, we did this test at a 5% level of significance, and you can see we didn't reject the null because our test statistic is not in the rejection region. And in this case, again, if we compare our p-value, we have quite a large p-value. We don't know exactly what it is, but it's much larger. Even the lower limit is much larger than alpha. So we can already say we're not going to reject the null hypothesis. But let's go now get the p-value a bit more accurately. So if we look at table 810 in your textbook, this is very similar to the t-tables I just introduced you to, where you have an upper tail area, and you have in the columns you have the different degrees of freedom, and on the left hand side this time, instead of having the chi-square values, you now have your probabilities, and the chi-square values are on the inside. So that's the only slight difference between the two, the t-tables and the chi-square curve tables. So again, what we want is the probability that y is larger than 22.875, and we need to consider 15 degrees of freedom. So we're only interested in this column. Then we need to go look for this 22.875, and we find it in between those two values there. So then that means if we go to the left hand side, we can find that probability. So we can see here that the probability that y is larger than 22.875 is between 0.085 and 0.09. And if you had forgotten that you need to still multiply by 2, if you compare it to the results from A6, you should immediately notice, but these don't even intersect. So there's something wrong. We haven't finished the question yet. So all we need to do is we need to multiply through by 2, and the inside bit, the one here in the middle, becomes the p-value because the p-value is 2 times that probability. And that tells us that our p-value is between 0.17 and 0.18. Sorry, I forgot to do that. That is not supposed to be there. So that's already multiplied in. And that is pretty much it. So let's go back to the question or the test procedure. So there we now have a much narrower interval for our p-value, and we can get the exact p-value again from R. Keeping in mind you've already done this in one of your practicals. If we want to calculate a probability from a chi-square distribution, we just use the p chi-square function. The first argument is going to be our test statistic value. The second argument is our degrees of freedom. And then again, I've specified that I don't want the lower tail probability, I want the upper tail probability. And it all needs to be multiplied by 2. And if we look at this value here, you can see that it does fall inside these intervals. So we know we haven't made a mistake. We've done it in 3 different ways. All of them agree with each other. The one is just more accurate than the other. But you can see that it all makes sense. It all fits together, and the p-value is not as it's not smaller than alpha, which means we don't reject the null. So we're still getting to the same conclusion. So when we do hypothesis testing with the p-value approach and with the critical value approach, both of those should give us exactly the same results. If you're getting different answers, and it typically happens in my experience when people are dealing with a two-sided test and forget to multiply by 2. So if you do a test, maybe it's a good idea to do both the critical value approach and the p-value approach, just to make sure that you get to the same results. And if you don't, you know you've missed something somewhere. So for this chapter, in section 9.4, we are excluding the section on interpreting p-values. You don't need to worry about that. I would suggest reading through it. It does give some insight, but don't stress, it's not going to be tested. Then also in section 9.5, 9.5 is technically excluded, but for future reference, it would benefit you to read about statistical versus practical significance. So it's very interesting to just read through, gives you a little bit of perspective, but we're not going to test you on it. It might just help you understand the problems a little bit better. And then the rest of that chapter is excluded. So these things, the best tests, the power of the test, all of those things, likelihood ratio test, those things are going to be dealt with when you go to second year. So we're not going to worry about that now. Then for homework, I want you to go work through all of the examples in section 9.4. I haven't looked at any of them now in the video. So you can go and work through those yourselves. And then calculate the p-values for the homework exercises I've given you before. So I found a little cartoon online as well where they explain p-values and how to interpret them. So hopefully this is useful to you guys as well. And that's pretty much it for chapter 9.